Everybody, the purpose of this video is to reinforce an idea from class that when you average grouped data versus averaging raw data, you do sacrifice some precision because you've lost some of the exactness of the data, but any loss of precision is basically negligible. The way I'm going to demonstrate this to you is I randomly generated some normally distributed data points. We'll talk more about this in class as time goes on, but basically data can have a shape, and the shape of the data, we spoke of this in class, last class. It can be bimodal, can be unimodal, can be multimodal, can be skewed, can be symmetric. If it's symmetric and unimodal and follows a certain shape, it's going to be what's called normally distributed or bell-shaped. So what you've got here in the blue region of the curve here are 1,000 data points broken up by what their value is, rounded off to the nearest whole number. So here you've got no zeros, no ones, 1, 2, 3 threes, 9 fours, 27 fives, and so forth and so on up to 20. So it's a nice bell shape. Behind it in red, I've done the exact same data, but I've grouped it in widths of 3. So there is one data point between 0 and 2, and that's that 1, 2. There are 39 data points between the 3 and 5. There are 225 data points between 43 and 101, and so forth and so on. And I stacked them back to back using Excel here. I think that's a fairly clear way of seeing what's going on. Now, what I'd like to focus on are these two averages over here. The average of the raw data is 10. The average of the group data is 9.943. Now, you might remember from class, we did a similar argument with our keys, where we averaged the raw numbers of keys versus the grouped number of keys, and they were only off by, I think, a tenth. Very similar to what these averages are off right here. Now, what's special about the spreadsheet that we're looking at right here is that this is a dynamic spreadsheet. So if I press the F9 button, we're going to get a whole brand new set of 1,000 random normally distributed data points. And FYI, I'm going to have you guys doing this kind of thing in 243 and also in 244 if you go down that path with me. So I'm going to go ahead and press F9. Notice the curve changed. The curve changed. We got ourselves a new curve, new bell curve. It's still bell-ish. I mean, it's not perfect. It's not perfectly symmetric. It's not as beautifully unimodal as it was before. The grouped data definitely is still almost perfectly symmetric and unimodal. But the individual data points are not. But check out the averages. Raw data still average perfectly 10. Group data is just over, a smidge over. Let's F9 it again, and again, and again, and again. And let's just go ahead and let it do its thing a few times. And you're noticing, each time I press F9, I'm getting a brand new set of data. But the data generally follows a bell curve shape, and generally almost always has the exact same shape. Sure, there's variances. I mean, 229 and 279 are off by 50. But generally, the data goes up and then falls back down in that predictable bell curve. And hopefully you noticed over here, as we were looking at the raw data versus the group data, sometimes it's a little bit above 10, sometimes it's a little bit below 10, but it never strays too far from that raw data average of 10. Now, why? And that's kind of the point of this whole argument, is why does it not vary all that much? Why is it that they're staying so consistently right near that center of 10? And if you look at the blue curve, I think that answers the question pretty well. Okay, let's look at the red curve with the blue curve. Red, 0, 1, and 2, there are no data points. That sums to 0. 18, 19, and 20, there's one 18, which means the sum of the three classes is 1. Okay, it's good enough so far. That's basically balanced. Then we come in here to 47 and 28. Okay, 47 and 28. We've overestimated the 47 compared to the 28. There's roughly almost twice as many data points in here as there are in here, which means we've got too many on this side compared to this side. And if you look inside the bins, because it's bell-shaped, we've got more of a rise going this way than we have a rise going this way. So this side of the curve is overestimated. Now look at the next bins, 227 and 247. Do you notice that there's more in the 247 than the 227? That means we're overestimated on this side compared to this side. In this case, the 100 bin is bigger compared to the 69. So although we had a few extra too many over here, that's canceled out by the few extra too many over here. And even this imbalance right here in the middle, the 149 to 129, is going to be gobbled up over time by the other inconsistencies on both sides. I mean, sure, the overall average is 9.955, which means we've got more on the left side than the right side of 10. But more, quote unquote, is kind of relative. It's not much more. Go ahead and press F9 again to reshuffle. Now we've got more on the right side than the left side. And you can see why. 56 to 41, 251 to 209. Okay? So definitely, this one seems a little bit more obvious. There's more on this side than there is on this side. But again, we're not straying all that far from that average of 10. We're not straying all that far from the average of 10. And that's what I find to be so interesting about the law of large numbers is it drops these data points into bins so predictably, yet we can't prove why it works. It just does. And that hopefully explains to you a little bit more about why the average of group data is a reliable indicator of the underlying raw data. Thanks for watching.